Lee. Today, I'm going to present our paper, Learning to Perturb Word Embeddings for Out-of-Distribution QA. This is joint work with Minki Kang, Juho Lee, and Ju Hwang. Recently, neural net with pre-trained and large corpora have achieved impressive performance on various input tasks such as question answering. However, they are fragile to distributional shift. They fail to predict the correct answer of the question, which falls outside of training distribution. For example, bird QA model have already surpassed human performance in squad dataset, but it often makes a mistake for answering question from Amazon review. But we want to build a robust QA model which generalizes to unseen domains. Data augmentations are known to be effective regularizer for improving performance on unseen domains. However, most of them are developed for image domain and they are not directly applicable to text data. Transforming data instance with a variety while preserving the original semantic is challenging for NLP tasks. A simple technique is replacing a word with synonyms. However, diversity of viable transformation is limited. Recently, Ng et al. Proposed a new data augmentation method with masked language model where we mask some of the words and reconstruct the masked one with pre-trained language models such as BERT. We can sample diverse examples, but it may change the semantics of the original sentence. While such change in the semantics may not be a serious problem for certain tasks, it could be critical for a question answering task since its sensitivity to the semantics of inputs. For instance, replacing a single word with a synonym might cause a drastic semantic drift of the answer. To address such limitation of the existing data augmentation techniques for QA, we propose a novel data augmentation method based on learnable word-level perturbation, which effectively regularizes the model to improve its generalization to unseen questions and contexts with distributional shift. Specifically, we train a stochastic perturbation function to learn how to perturb each word embedding of the input without changing its semantics and augmenting training data with the perturbed samples. We refer to this data augmentation method as stochastic word embedding perturbation, in short SWAP. So we want to learn distribution of noise such that perturbation does not alter its semantics. To this end, the likelihood if the answer should be kept high even after the perturbation. That is, we need to maximize the conditional log likelihood P of y given x and z. Moreover, we want to inject the prior knowledge that the perturbed input is close to the original input x in average. So we want to minimize the KL divergence between noise distribution and prior distribution, where prior distribution is a Gaussian distribution of which means is 1 and some diagonal covariance matrix. As described earlier, we can jointly train the QA model and noise generator to maximize the objective. However, we want to train the QA model with additional data drawn from different generative process as well as the given training data to increase the support of training distribution, which leads to better regularization and robustness to the distributional shift. Therefore, our final objective function is convex combination of two functions. Moreover, we can simply show that our proposed noise form is a function of Gaussian dropout and input x, which scales and translates the Gaussian dropout mass depending on the input words. The parameterization of the perturbation function heavily affects the success of learning with the proposed objective. The function is to control the intensity of perturbation for each token of x without changing the semantics. Since the meaning of each word varies across linguistic contexts, the function should be expressive enough to encode the sentence x into a meaningful latent space embedding to contextualize the subtle meaning of each word in the sentence. To this end, we share the encoder function to contextualize the input x into hidden representation and fit it into the perturbation function as input. However, we stop the gradient of phi propagating to the encoder f. Intuitively, it prevents noisy gradient from flowing to the encoder for early stage of training. On top of the encoder, we stack 2-layer feed-forward neural net with ReLU activation, which outputs mean and variance for each token. Then we sample noise from Gaussian distribution and multiply with word embedding ET for each time step. In experiment, our goal is to show that the swap is effective regularizer under domain shift scenario. As we mentioned before, our goal is to regularize the QA model to generalize to unseen domains. So we train the QA model only with squad trained dataset, then evaluate the trained model on squad depth dataset to measure the in-domain performance. Moreover, to validate the out-of-domain generalization performance, we use 5 different datasets. We perform experiment with our model swap and its variant prior aug, which augments the data with a noise from the prior distribution against several data augmentation methods. Adversarial augmentation perturb the word embedding with an adversarial objective, and both Gaussian and Bernoulli dropout perturb the word embedding with a masked sample from each distribution. Word dropout randomly drop the word, then set the selected word embedding as a 0. Simba masks some of the words and reconstruct the masked one with pre-trained language model and use the reconstruct sentences as additional data. In our experiment on the extractive question answering task, our model outperforms most of the baseline with pre-trained language model, namely BERT and Electra. In addition, in our experiment on the generative question answering task with T5 model, our model consistently improved the performance against baseline. We empirically show that our data augmentation swap is also an effective regularizer in the low resource setting. We trained the model with a subset of squad dataset and measured the performance of out-of-domain performance as well as in-domain performance. Our model consistently improved both in-domain and out-of-domain performance, although it is trained with much fewer samples. The question-answer pair generation is considered as a representative method for data augmentation in question-answering tasks since it can generate the plausible question-answer pair from given the context. In this experiment, we showed that swap is sample efficient and further improved the performance of the QA model trained with additional synthetic data generated by the recent question-answer pair generation model called InfoHCVA. Specifically, the QA model plus swap trained only on the squad dataset already outperforms the QA model trained with about 240,000 synthetic QA pairs. Moreover, when combining two methods, we achieve even larger performance gains. And we further perform an evaluation study to verify the effectiveness of each component of swap. We observed that the non-learnable noise generator generally performs worse than our full model with a learnable noise generator. Furthermore, we find that the use of noise and MLE objective together is crucial for performance improvement with swap. For analysis of our model, we first quantitatively analyze the noise generated from the swap model by comparing it with other baselines. Since our major motivation is to design the data augmentation method which preserves its original semantics, we simply try to check how many words are trained by each data augmentation method during training. For latent perturbation methods such as adversarial augmentation and swap, we find the nearest word of perturb embedding in the word embedding space. For qualitative analysis, we visualize the L2 distance between the original word embedding and the perturbed word embedding. We observe that the perturbation function learns to generate adaptive perturbation for each wall. In conclusion, in this work, we propose a simple yet effective data augmentation method based on stochastic word embedding perturbation for auto-distribution QA tasks. Our stochastic noise generator learns to perturb the adaptive noise depending on the contextualized embedding for each word, preserving the original semantics. We validate swap on dataset from 5 different domains, then verify that our method improved the robustness to distributional shift, outperforming the baseline data augmentation method. Thank you.